Welcome to Safety Engineering Briefings. Short, practical insights for software and security engineers. We had a production incident last month. A seemingly minor code change in our order processing system caused a cascading failure. Orders weren't being fulfilled. Customers were getting error messages. It took almost 12 hours to fully recover. The root cause wasn't a bug in the new code directly. It was a hidden dependency we hadn't accounted for, and a lack of understanding how that dependency would react under load. That's where safety engineering comes in. It's about anticipating those hidden interactions. Most engineers think of safety as preventing crashes or handling errors gracefully. That's important, but it's reactive. Safety engineering is proactive. It's about designing systems to avoid dangerous states in the first place. Think about it like this. Reliability is about making things work when they work. Safety is about making sure they don't break in ways that cause harm. Harm can be data loss, financial loss, or even physical harm, depending on the system. A common misconception is that safety is just testing. Testing finds problems. Safety engineering tries to prevent them. We do this by systematically identifying potential hazards. Hazards aren't just bugs. They're conditions that, combined with a particular event, can lead to a negative outcome. For example, high network latency is a hazard. A poorly designed retry mechanism is a hazard. The combination of the two could exhaust resources. We then analyze the risk associated with each hazard. Risk isn't just probability multiplied by impact. It's about understanding the severity of the impact. A small probability of a catastrophic failure is still unacceptable. We then implement mitigations. Mitigations aren't just workarounds. They're changes to the system's design to reduce the risk. This often involves adding redundancy, limiting complexity, or introducing safeguards. It's about building in resilience, not just reacting to failures. Let us consider a typical e-commerce platform, specifically the inventory management system. It's a distributed system using a microservices architecture. Each microservice handles a specific aspect of inventory, availability, reservations, adjustments. A common failure mode is a race condition during peak sales. Imagine a popular item goes on sale. Multiple users simultaneously try to purchase it. The reserve inventory service gets flooded with requests. If the database transaction isn't carefully designed, it's possible to oversell the item. The consequence? Angry customers, order cancellations, and potential financial losses. A typical fix is to add retries. But retries, without proper rate limiting and idempotency, can worsen the problem. They amplify the load on the database, increasing the chance of a deadlock. A safety engineering approach would involve analyzing the potential race conditions before deployment. It would involve designing the system with optimistic locking or using a distributed consensus algorithm to ensure inventory consistency. It's about preventing the overselling scenario, not just handling it after it happens. Safety engineering isn't about making systems perfect. It's about understanding how systems can fail and designing them to fail safely. It's a shift in mindset from reactive problem solving to proactive risk management. Consider this. What assumptions are built into your system's architecture that, if violated, could lead to unexpected and harmful consequences? If this topic was useful, take a moment to reflect on how it applies to your own systems. See you in the next briefing.